So in this chapter, we'll look at electromagnetic induction and electrical devices which exhibit that effect called inductors. Just a couple of little quick reminders from last chapter. If you've got a wire with a current passing through it, you can figure out the direction of the magnetic field due to that current just by using the right-hand rule. And if you're interested in figuring out the magnitude magnetic field, you can use Ampere's law or even Biot-Savart. And you'll get, of course, mu naught I over 2 pi r, where r is the distance away. For a loop of current carrying wire, right around in the middle here, if this thing has a radius of r, you can very quickly calculate, again using Ampere's law, or Biot-Savart, probably easier, mu naught I over 2r, where in this case capital R is the radius of our loop. We'll give you the magnitude of the magnetic field in the middle of this. For a solenoid, again remember solenoid's a very concentrated field in the center, and we came up with this very simple equation where the small n here is a number of loops per unit length. And then finally a torus, magnetic field basically is concentrated inside. Why? It's like a solenoid with the two ends meeting. And using Ampere's law, you can come up with the magnetic field inside. It does vary with r, but where n is the number of loops and r is a distance away from the center. Very concentrated near the middle, a little bit less towards the outside. So, now taking it back a little bit. Remember that in 1820, Hans Christian Ørsted discovered that electric currents produce magnetic fields. Remember, he put a wire across the compass, and when the current flowed, the compass needle would move perpendicular to the wire. At that point, everybody knew, okay, electric currents produce magnetic fields. Hey, I wonder if magnetic fields can produce currents. And immediately, everybody went to work. They thought, oh, this is going to be obvious. We're going to have it before the end of the year. And then 6 months went by. Nobody had found anything yet. And they tried everything. Wrapping wires around magnets, different directions. Nothing seemed to work. A year went by. People are starting to doubt. 2 years went by. All right, now things are getting serious. 5 years went by. 5 years without a discovery in a field is basically a death warrant. 10 years went by. At this point, most people had given up any hope that we could use magnetic fields to produce electric currents. And then, our favorite janitor, Michael Faraday, 11 years later, discovered that magnetic fields could produce currents. Now you might say, why in the world did it take so long? Well, it took somebody with some skills to actually produce basically the world's first galvanometer and actually make coils of wire that would actually work. How did it work? Well, let me show you this quick little video. The simplicity, now that we look back, is crazy simple, but at the time, it was a very difficult experiment.
A simple loop of wire. My job is to make an electric current run around in this loop. The loop is connected to a galvanometer whose output is that point of light on the screen. So if I succeed in making the current run through the loop, that light will move back and forth on the screen. How am I going to make it work? Well, I've got to do it using magnetism. So here I have a bar magnet. To use this bar magnet to make a current run around in this loop is very easy. All I have to do is to move the loop into the magnet, or for that matter, back out again. That was it. That was the great discovery. Oh yes, and incidentally, one thing more. If I move the loop back and forth like that, then the current runs back and forth and keeps on going. Well, virtually all electric power, one way or another, is generated by that mechanism. In other words, that discovery is the very basis of our electrical civilization. And that's our subject.
For today. Almost all the electrical power we use is generated by electromagnetic induction. There's a few isolated differences. For example, solar power, if it's using solar panels, is actually produced by a different method. But everything that involves generators is using this technique to produce it. How does it work? Well, take a look at this situation. We've talked about this before, but in this region here, the magnetic field is pointing into the page. And we've got a wire, which is this light shaded blue thing here, that's moving towards the right with some velocity. Now, take a look at one electron inside of this wire. Remember, the electron's free to move. If you do your right-hand rule, current, field, force, you'll discover the current is pointing towards the left because the wire is moving to the right. Field is into the page, and the force, due to the magnetic field, QVB, is going to be acting down this way. So this is the force due to the movement for the magnetic field. The electrons are going to get forced to the bottom. As that wire moves, more and more electrons are going to pile up along this end of the wire, leaving the top edge of the wire slightly positive. Now, because of that positive charge up at top and the negative charge down below, the electron's also going to feel a force upward. Once it reaches equilibrium, we've got this force due to the electric field acting upward, F sub E, and the force due to the magnetic field acting downward. And at some point, we'll reach equilibrium. And at that instant, we'll have a constant electric field that's going to be pointing from the positive towards the bottom. The question is, first of all, what is that electric field? And then, what would be the potential difference between the two ends? Well, just again, in this case, I'm going to hook a resistor on the outside of it, of resistance R. Let me complete the circuit here. There we go. So we've got a resistor R on the outside, completing the circuit as this wire is moving. You can imagine the resistor moving along with the wire. So we've got this. We've got the force due to the electric field, which will be Q times E. Just remember rewriting the definition of electric field. And we've got the force due to the movement of the charge through the magnetic field, QVB. Cross product here not so critical because it is 90 degrees between the velocity and the magnetic field. When it reaches equilibrium, what has to be true? These two have to be equal to each other. Well, plugging in our numbers and ignoring the sign this time because of the perpendicular part, we'll discover that the electric field is equal to the velocity, small v, times the magnetic field. So what's the potential at that point? Remember, voltage is just equal to the electric field times the distance. We usually write it as E dot ds. But in this case, we know that, and I'm interested in the magnitude, so I'm dropping the negative sign. The electric field in this case is constant, just equal to V times the velocity times the magnetic field. So in this case, I can skip the integral and just write it as VBL. And that's going to be the potential difference, or the induced EMF produced in this wire. And you're going to see this particular expression appear in a lot of different places in this chapter. Velocity times the length of the wire that's perpendicular to the motion times the magnetic field will give us the induced EMF, the induced voltage. Even though there's no batteries in this circuit, there is an induced current. Using Ohm's law, current is equal to the EMF, or voltage divided by resistance. In this case, our EMF is VBL from up above here, and our resistance R. There will be a current flowing through this loop. In this case, clockwise. From positive here is going to try to go back to the negative, and we're going to end up with, it's acting just like a battery with a positive and negative terminal. This is the way you produce electricity. You're like, well, wait, this is hard to do every single time doing all this work. Is there an easier way to get there? The answer is yeah, you betcha. But first of all, Faraday's experiments. He discovered a couple of things. The current only appears if there's relative motion between the loop and the magnetic field. The current disappears when the relative motion between them ceases. If you don't have the magnet moving relative to the coil, there is absolutely no current, which is why all the experiments where they just wrapped wire around the magnet without moving the magnet failed. Faster motion produces a greater current. The faster you move the coil or the magnet, the greater the induced EMF, and therefore the greater the current. If moving the magnet's north pole towards the loop causes a clockwise current, then moving the north pole away will cause a counterclockwise current. Moving the south pole towards or away also causes current, but in the reverse direction. And here's the big idea. Faraday basically realized an EMF is induced in the loop when the number of magnetic field lines that pass through the loop is changing. That's the way he thought about it. We've got a way to describe field lines going through closed areas, and that's usually what we call flux. So we could take Faraday's basic idea here and just say the magnetic flux is changing. So how do you calculate the magnitude of the flux? Well, you just take the magnitude of the magnetic field times the area of the loop. And again, just a quick reminder on this one, we typically draw the area as a vector that is perpendicular to the surface. And again, it's sort of normal to it if you want to think about it. But that's the area vector. And you might say, well, which side of this should you draw? That's a little bit trickier. Normally, with electric field lines, remember, we always drew the area vector on the outside of the closed surface. For magnetic field, we'll worry about that later. So here's the definition of magnetic flux. Still using phi for flux, but this time with the sub b to represent magnetic field. It's just the integral of b dot dA. Magnetic flux is a scalar quantity. It is not a vector, just like electric flux is also a scalar. Nice enough, in a uniform magnetic field, we don't have to use the integral notation. We can simply do this. And by the way, this is a dot product up here, which means, yes, we have to use cosine of theta. The units for magnetic flux are the units for magnetic field, teslas, times the unit for area, meters squared. So the units of magnetic flux are Tesla meter squared. It's also given its own unit called the Weber, abbreviated capital W small b. But again, don't worry about that one. We don't use that too often. So here in this case, you can very quickly find it. Which one of these two would have a greater flux, assuming both of them have an area of A? The answer, of course, is this one here, because the angle here is 0 or 180, depending on which way you draw it. But in this case, there is a phi or a theta. In this case, this is the area vector magnetic field over that way. The angle between here is going to reduce it. So here it is, a real practical example, this time with numbers. A rectangular coil of wire is situated in a constant magnetic field whose magnitude is 0.5 teslas. The coil, represented in this case by the black rectangle, has an area of 2 square meters. Determine the magnetic flux for the 3 orientations shown, 0 degrees, 60 degrees, and 90 degrees. Just in this case, plugging and chugging. Just again, remember, we draw in this case, they actually tell us to draw the normal line along here. This is our area vector. Here's our area vector. And here's our area vector. And so solving this one is literally just plug and chug. For the first one, it's just going to be B, so we're using this last equation here. Magnetic field 0.5 times the area 2 times the cosine of 0 degrees gives us 1 Tesla meter squared, or 1 Weber. The second case, plugging and chugging, cosine of 60 degrees is 1/2, and so we get a half, or 0.5 Tesla meter squared. Last one, of course, cosine 90 degrees is 0, and so our flux, magnetic flux, is 0 Webers. So, magnetic flux, okay, you got it, it's interesting, but in it by itself, it's not terribly useful. So where does it become useful? Why are we talking about it? Well, remember Michael Faraday's experiments. The idea that moving a magnet towards a coil of wire can produce an induced EMF. Here's where the two things tie together.
For example, he could induce a current by moving a bar magnet relative to a coil.
This is his homemade galvanometer. magnetic needle above a coil of
And when
wire.
Faraday connected a coil to a battery, the sudden increase in the magnetic field induced a surge of current in another coil. Both these ideas can be expressed in terms of magnetic flux.
So here's the definition of
The
flux
total
again.
magnetic flux through a surface is the integral of the component of magnetic field perpendicular to each bit of area that makes up the surface.
Case technically a double integral because we're integrating across areas.
As a loop of wire moves through the field of a bar magnet, the flux through the loop keeps changing.
Area is
The
constant.
changing flux causes a current to flow as if it were driven by a voltage.
The magnetic field magnitude and angle keeps changing.
That voltage, called the electromotive force, E, is equal to minus the rate of change of magnetic flux through the loop.
This is the big idea.
That's called Faraday's law of electromagnetic induction.
The change of magnetic flux with respect to time gives you the EMF. That idea is really quite powerful. And you might say, wait, why is there a negative sign there? Well, we'll talk about that one a little bit later when we talk about Lenz's law. But for right now, just go with this. The induced voltage or induced EMF is simply equal to the change in magnetic flux over the change in time. If you had, that's for one loop of wire, if you had multiple loops and phi sub b was the flux through one loop, if you have, for example, 10 loops, it would be 10 times the flux in one loop. So adding more loops causes a greater change in flux over the same amount of time. If you're dealing with a uniform magnetic field, you can actually rewrite it this way. Remember, flux is BA cosine theta, and as long as it doesn't vary, so we don't have to do an integral, we can simply write it this way. So then the question is, all right, so how can you produce a voltage? Well, you need to have a change in this quantity. And there's a couple ways you could do it. One is you could change the magnitude of B. That, of course, make the magnetic field stronger or weaker. That would create a change in this with respect to time and therefore a voltage. Or you could change the area of the loop. Changing the area with respect to time would also do that, squeezing your loop together or stretching it out. Or, of course, you could change the angle, theta. That, of course, would cause a change in the flux. So you could rotate your loop in the magnetic field, for example. Or you can vary any combination of those, or all of them if you want. All of those would produce a voltage, which is kind of fun. Please notice the more rapidly you change this, the smaller the dt, the greater the voltage you'll produce. Why do I bring that up? Well, we'll talk about that in a second. Here's a quick thought check problem. Which of the following will not cause a current to be induced in this green loop of wire? Magnetic field is uniform into the page, but only in the region I have shown. So here it is, pushing the loop out of the field. Here's pushing the loop into the field. That's E. Which one of these will not produce a change in magnetic flux? The answer is, if you haven't quite figured it out yet, is C. If you would just keep the orientation of this green loop constant, but then move the green loop straight out of the screen or into the screen, it would not change the flux through it, assuming the magnetic field is uniform. All the rest will somehow modify it. Another quick example. Say in this case we're not moving the green loop, but we are varying the magnetic field with respect to time. So this is a graph of the magnetic field through this loop with respect to time, t. In which region is the magnitude of the induced EMF the greatest? Well, if you take a look at this, in this case, area is constant, so I can move that outside the integral. The cosine is 0 degrees, so I can move that or ignore it, basically make it 1. And so I can basically rewrite this thing as this. It's the rate of change of its negative area times the rate of change of magnetic field with respect to time. In fact, I'd almost rather write it just this way, dB dt in this case. So in what region of the graph is there the greatest voltage produced? Well, it's the area or the region which has the greatest slope, dB dt. Where's that going to be? The correct answer is B. Even though the magnetic field is greater up here, it's not changing. In fact, there's no induced EMF in C. And D and E have the same, but that slope is smaller. And it's negative, which actually would create a current one direction when it's increasing, a current the other direction when it's decreasing. Another quick check. A coil is placed in the magnetic field and the normal to the plane of the coil remains parallel to the field. Which one of the following options causes the average EMF induced in the coil to be as great as possible? So just so you can visualize it, you've got a loop here. Magnetic field lines are going straight through it. And we're not changing the orientation of the loop, but we are changing the field. So in this case, the magnetic field is varying. Which one of these is going to produce the greatest change in flux? When the magnitude of the field is small and its rate of change is large, the magnitude of the field is large and the rate of change is small. The magnitude of the field is large and does not change. Hopefully you realize in this case, it's the slope of the magnetic field versus time that's going to produce the greatest EMF. Again, you could rewrite this equation as, if area is constant, move it outside, it's the rate of change of the magnetic field with respect to time that's going to create the greatest EMF. In this case, which is the right answer? The answer is, of course, A. Something just fun to think about. We've talked about this. You may have heard of EMPs. It's electromagnetic pulse generators. The idea is that these are non-lethal weapons that you can use to take out an enemy's electronics or their entire power grid. It works on this very simple idea of the EMF is simply equal to the rate of change of the magnetic flux with respect to time. In this case, how does an EMP work? And no, you can't build this as your final projects. Is this. In this case, there's a large capacitor remote bank over here. The idea here is it can produce a very large current for a short time. You close the switch, the current, a very, very large current, to the point where it probably would almost melt this solenoid to try to get maximum field. Don't worry, the current's not going to last very long because that thing's going to produce a very, very large magnetic field. Inside of the solenoid, we've got a copper cylinder with a slit in it. And surrounding this entire thing, we've got plastic explosive. You're like, wait, who ever thought of these things? Well, the plastic explosive is going to implode the solenoid and the copper cylinder. What is that going to do? It's going to take the flux from what it is now, which is very large, to zero, basically, in an incredibly short time frame. Millionths of a second, microseconds. What is that going to do? It's going to produce an incredibly large voltage, which is going to be expressed across this tiny little slit. That kind of electric field produced by this very high voltage over the short distance, remember again, electric field can be written as the change in voltage over the change in distance, is going to create this incredible field which is going to spread out from this device in all directions. When that interacts with electronic devices, it's going to induce a large voltage. Remember, electric field times distance. If you've got a long section of wire, the voltage induced on it is going to be E dot L, where L is, or times length, where L is length of this wire. For power grids, those wires are usually fairly long, and so the voltage induced is incredibly large. But it also even works on small electronics. So first of all, let me show you an old video clip here from Ocean's 11, where they used an EMP generator to take out the power in Las Vegas. In reality, there was talk of them at the time, but in reality, they were not real things yet. Here is an unclassified view of an actual EMP running on a computer lab. So take a quick look at this one.
When that computer went out, when we fired, it actually took out the cameras as well. We took out everything on that. It was fantastic.
Well, one part I wanted to show you if you didn't see it. If you watch this CD player, the CD drive opens while the CD is still spinning, and so you get this little frisbee effect if you watch this again backwards. This is an old clip, but it's still amazing. So here's a sample question. You've got a long blue solenoid S that has 220 turns per centimeter and carries a current of 1.5 amps. Its diameter D is 3.2 centimeters. At the center, we place a 130 turn closely packed coil C, it's the yellow one, of diameter 2.1 centimeters. The current in the blue solenoid is reduced to zero at a steady rate in 25 milliseconds. What's the change or the magnitude of the EMF that's induced in the coil while the current in the solenoid is changing? All right, just be able to solve this one. First of all, remember, you've got a magnetic field going through the center of this blue solenoid. And remember, you can calculate that just by mu naught n I. In this case, I wrote it n mu naught I. Remember, the n in this case is the number of turns per length. In this case, specifically, number of turns per meter. Because this is the number of turns, you've got 220 turns in 1 centimeter, multiply that by 100 to get the number of turns in 1 meter. Times mu naught times the current, which is 1.5 amps. So what's the magnetic field on the inside of this thing? The answer is the magnetic field is not crazy large, 0.0415 teslas. And again, remember, it's fairly uniform. Well, that same field is passing through this yellow solenoid that's in the center. If you figure out the area of one loop of this, it's just going to be pi r squared. Where in the world did I get this number? Well, that's half of the diameter that's shown here. So 1.05 centimeters, written as meters down here. And so the area of one of the loops on this thing, just one of them, would be given by this. So what's the total flux through this thing? Well, it's going to be the flux through one loop, the magnetic field times the area, times 130. Where's the 130 come from? Well, there's 130 turns in that yellow solenoid. So the total flux going through it is given by this, 0.00187 Webers, or Tesla meters squared. Finally, last step. What's the EMF produced? Well, this magnetic flux that we just calculated is going to go from this down to zero in this amount of time. Technically, I guess it would be a negative change, so we got a negative as well. Whoops, that should be equal as a negative of that. And since we're looking only at the magnitude, that's the size of the voltage, you get our answer, which is this, about 0.0747 volts. Not huge, but you can actually get a small voltage induced. You can see why Faraday had such a hard time producing it, especially with the tools that he had available to him at the time. So take a look at this. Let's take a look at that same circuit that we showed sort of at the beginning of this section or this video. In that one, we moved the wire through it. There's another way of doing it as well. In this case, you've got two copper conductors on each side here. That's sort of the yellow ones. You've got a resistor connected across it with a wire. And here you've got, and it's kind of hard to see, this blue thing here is a metal bar that's rolling across it with some initial velocity towards the right. And you might say, whoa, 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 does that still have a flux through it? That's going to produce a voltage? Yeah, think about it. In this case, again, we can now use Faraday's law to actually come up with that. What's the magnetic flux? Well, if you look at this, the magnetic flux is going to be given by our distance between these two, which is x. Well, magnetic flux is going to be magnetic field times the area. That's x. This is L, the length of our rolling wire, and the distance between the two copper plates. And so the area is just L times x times the magnetic field. Oh, there we got our flux. If we look at Faraday's law, we know the change in the magnetic flux over time is going to give us that. In this case, L is constant, B is constant. We can move those outside. And you may not see it right away, but if I just move, let me do one more step here. It's going to be equal to negative B times L times dx over dt if I move the two constants out front. Well, dx dt can be written as, yes, you guessed it, velocity. And so what's the EMF in this case? Well, it's just BLV. You're like, wait, that's the same answer we got for a moving wire, or for just a piece of wire moving through it. Yep, it's the same. Then what's the current in this loop? Well, it's just going to be the voltage over the resistance. You saw that before. Now, there's something interesting going on here. We could even calculate the electrical power. The electrical power, you can use V times I, or V squared over R, or I squared R. I'm going to use I squared R for this one. The current we know is for this times R gives us this expression for the electrical power generated. But I've got a question. If this is the electrical power coming out, is that equal to the amount of power that we're putting in? Now, you can quickly calculate if the current's going this way, and using your right-hand rule, current, field, force, the force due to the magnetic field on this wire is going to be this way, ILB. That's on the whole wire, not talking about just a charge inside. So to keep it moving at a constant rate, I'd actually have to put an applied force that would be equal to it this way. Otherwise, this wire would very quickly slow down. Well, in this case, what is that force? Well, it'd be ILB times the sine of theta. In this case, just ILB. And if you work it out real quick, remember, power is equal to that force we'd have to apply. The applied force would be equal in magnitude to this times the velocity. Remember, one of the more unusual formulas for power was force times velocity. We haven't used it very much. In this case, if you work it out, you'll come up with the force, ILB, times the velocity of the thing, that. And if you multiply that out, you'll get this. Oh, look at that. The power we're putting in by applying our force is exactly equal to the electrical power we're getting out. Yes, you don't get anything for nothing. All the energy we put in gets converted to electrical energy, or in this case, eventually ends up as heat. Lenz's law is the last thing I want to talk about. Remember that negative sign we talked about here in that equation, and I promised I'd tell you about it? The negative sign here really doesn't affect the magnitude, but it's based on this idea that Lenz discovered. Lenz, L-E-N-Z, discovered that the induced current in a loop creates a magnetic field that always opposes the change in magnetic flux. What produces that current? Well, it's the voltage, or the EMF. And so the induced current, or induced EMF, induced current, is always going to oppose the change in flux. And that's what this negative sign comes from. And you're like, whoa, 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 whoa. The big idea is you could think about it this way. The induced current tends to keep the original magnetic flux from changing. And it's a strange idea. So take a quick look at this one. In this case, if you're moving a bar magnet, can you see a north and south pole, towards this orange loop of wire, more and more field lines are going to be passing through it this way due to the magnet. The induced current in this loop is going to be running around this way. And if you check with your right-hand rule, that's going to produce a magnetic field that's pointing outward. what's it doing? It's producing a magnetic field that opposes the increase in field going towards the right. The induced current always creates magnetic, or tries to keep the magnetic flux from changing. In this case, if we move the bar magnet away, there'll be less and less field going through it this way due to the bar magnet. So in this case, the current actually is going to flow around this way. Why? It's going to produce a field that actually augments or adds to the field from the magnet that's slowly dissipating as it gets pulled away. So in this case, it's actually trying to add to it, as opposed in this case, when it was getting greater and greater, it was producing a field that was pointing outward to try to oppose that. That's the big idea of Lenz's law. Let me give you a couple of quick examples. In this case, if you move the magnet towards this loop of wire, and I hope you can sort of visualize the 3 dimensions, if you check your right-hand rule, the magnetic field now, due to this loop, is pointing this way through its center. As if you want to think about it, as if it has a North Pole that way. North Pole approaching another North Pole, they're going to repel. It always opposes that change. Another way of thinking about it, as this thing approaches, the field lines coming from this way are going to send more field lines through this thing this way. And this is trying to oppose it. Basically, Lenz's law will always repel, or the current produced will always repel any incoming change, or oppose any incoming change. In this case, it's actually going to exert a force on this magnet that's going to repel it. And you might say, whoa, why does that always have to be true? Well, think about it. What if the current was in the other direction? Well, that would actually attract the bar magnet, which would make it fly towards the solenoid, which would create a greater change in flux with respect to time, which would produce a greater voltage, which would produce a greater current, which would produce a greater magnetic field, which would attract the accelerating magnet even more, and very quickly you run into a runaway effect. It just gets greater and greater and greater. In this case, it's conserved. To actually put this or push this towards this thing is going to take some work because it's repelling. And we're producing electricity. And so you've got to do work to get energy, in this case, electrical energy. What if you had a bar magnet and you're moving it away? In this case, the current induced is going to produce a magnetic field pointing this way. And you might say, whoa, why is it going the other way now? Well, it's actually trying to augment the field that's dissipating as this field moves further away. But it's also doing this. It's almost as if the solenoid is now a bar magnet looking like this, with the south pole there. What's happening? As I'm trying to move this bar magnet away, it's actually being attracted. And so I actually have to do work to move this thing away from this. That's Lenz's law. Kind of a fun idea. All right, so take a look at this one. If I move the magnet there, we get a motion opposes it. Here, going that way, again opposing it. What we've talked about. So here's the big idea. The induced current always flows to oppose the change in flux. And I want to stop with one more slide, and this might be a little bit too much, but we'll come back and review it. So in this case, you've got a coil of wire. The thicker side is the outside of the screen because you have to kind of draw these in 3 dimensions. Only one of these cases is reasonable. And my question is, which one? So in this case, the magnet's not moving, and we've got a current flowing this way around the loop. In this case, it's moving towards it. The current's also flowing this way around the loop. In this case, it's moving away from it. It's flowing this way. In this case, it's moving away from it from the south pole, and it's going this way. In this case, the south pole is moving towards it, and the current's this way. Only one of these obeys Lenz's law. Which one? And I'll let you pause the video at this point if you want to think about it before I give away the answer. In this case, here's the answer. That induced current produces basically, if you use your right-hand rule for currents, produces a south pole here. What's that going to do? Well, it's actually going to attract the incoming magnet. That's not the way it should be. If you check this one with your right-hand rule with the current, it's going to produce a magnetic field that's acting this way. This is actually going to repel it, this magnet. And so as you're moving away, it's actually going to go faster and faster and faster. Also not quite right. In this case, that induced current is going to produce a magnetic field as if there's a south pole there. A south pole there, again, producing a force this way. It's moving away, and somehow magically this is going to make it go even faster. This last one, if you check the current, that induced current is going to produce a magnetic field like this. That's producing a repulsive force, acting against the velocity. And yes, this one will obey Lenz's law. Homework tonight, pretty straightforward. You're going to be using electromagnetic induction, Faraday's law, to do a couple of calculations. We'll spend more time with Lenz's law next time. See you soon.